The first part of this lecture is dedicated to talking about the origins of soil. Where does soil come from? Is it just always been there and it just moved around by water and wind? Or is it actually being created? New soil is being made in some places, or in other places maybe it's being taken away. So all good questions. There's soil almost everywhere on the planet, but not everywhere, but a lot of places. One of the places you might not think of it being is underwater. So there is what we would technically call soil is at the bottom of the sea, especially in less deep areas, shallower. And there's also soil high up in the tops of peaks of mountains, less there than there is down below and in the valleys. So it's everywhere. And certain processes of called weathering are what break down rocks into smaller particles, and some of those turn into parts of the soil. A big part of the soil too is organic matter, and that just comes from the bodies of dead organisms, including plant roots too that grow and die and leave their leftover roots dead in the soil. That's organic matter. So are dead bacteria and fungi, leaves, worms, things like that. And the fecal matter of all those things too add to the organic matter of the soil, which combines with the minerals and the rocks and the air and the water and the microbes to make up soil. But it's a process called weathering that creates new soil, and weathering from rocks down into smaller particles that become soil. So a couple of questions here at the bottom of the slide. What causes one soil to be productive and another one to be poor for crops? It's a good question. Right kind of off the top of my head, I would say the more organic matter it has in the soil, then usually the richer it is for supporting plants, but also the microbial community, the living things, especially the bacteria and the fungi, the more of those are held in the soil, which relates to how much organic matter is in the soil, means it's going to be more fertile, better for crops. Also, the minerals themselves. All soils need some amount of clay, not all soils, I should say, but most soils, and especially if you want your soils to support plants. Clay is, you don't want too much clay, then it's too heavy and hard and thick and dense. But a certain amount of clay, around 25 to 30% is not a bad amount. Clay holds on to a lot of plant nutrient molecules, and it also holds on to water. So that's good. If you have too much clay, it holds on to those things too tightly and doesn't let go, but just the right amount. The clay can store those things and provide the minerals and nutrients and release them to the plant. So in this picture, what are the rocks doing? Why are they there? We don't really know, and you can't know that from just looking at the picture. Like, where do those rocks come from? Do they come from way down in the mantle of the earth, or were they washed down from a higher rocky peak? Can't know, but we probably can guess that these are in the process of weathering into smaller particles. Just because trees are growing through them, the roots will break those rocks down further, and so will the water, and a bunch of different actions that create soil that we'll talk about next. So weathering is the process by which all rocks on the Earth's surface get broken down and turned into soil by becoming smaller particles. There's three types of rocks in general. You might know that from past education: sedimentary, igneous, and metamorphic. Weathering occurs by two main processes: physical processes, which kind of like what you think about, just breaking down the rocks into smaller pieces. But there's also chemical processes which break the rocks down into smaller pieces. So physical and chemical. We'll go into detail on those in the next slides. Bedrock, when it's exposed, so bedrock is the deeper solid rock layer that are older, and they do not contain soil, but they usually underlay soil. Sometimes they're exposed, like if you look up at the top of the front country here in Santa Barbara, you'll look up at the peaks and you see a lot of tan-colored sandstone. That's bedrock. There's also some Monterey Formation that has some shale. Those are bedrock layers that have been lifted up and pushed up to be exposed. But when that like our peaks here and other places like in the Sierra Nevadas, you have big outcrops of granite. When those are exposed, they're exposed to weather, and weather includes precipitation, snow, heat, cold, wind, and excuse me, even plants can help weather soil or weather bedrock, and break it down and help soil start to form. Over time, like in the picture on the left, you've got bedrock, and then slowly the bedrock you got precipitation that will cause some chemical breaking down or weathering of that bedrock into smaller chunks, and you get some plants starting, which they contribute organic matter to those broken up rocks, and also the moisture, because there's organic matter, that kind of early immature soil starts to hold more water, and the water itself causes breaking down of the rocks even more, and the buildup of organic matter, and the more the plants grow, the more they do that, and the more they can grow and add more organic matter, like you see in the third little section there. And you see bigger plants grow and more topsoil, the orange layer, forming, and it just kind of builds on itself, and it snowballs until more and more soil forms and organic matter and plants, and it's on its way to becoming a true soil. Let's look at physical weathering first, a little more detail. So there's 4 types of physical weathering. The way larger rocks get broken down into smaller pieces. Their chemical composition of the broken down pieces is the same as the bigger chunk that they came from. That physical weathering can happen in 4 different ways: freezing and thawing, abrasion, biological, and exfoliation. So the first one, in areas where, especially where it gets really like high elevation, and it gets really cold at night, and then relatively really big swings of cold and heat during the day. So you get warm at night, warm during the day, really cold at night, especially freezing temperatures. Water inside the little around rocks and in the cracks of rocks, really microscopic cracks, freezes and thaws. And that over and over again, that water in the cracks of rocks freezing and expanding and thawing and contracting over and over will break rocks up and physically weather them. Abrasion is where water, wind, and ice are exposed to smaller chunks and little, maybe airborne sand or particulates and sediments in water. Anything that's scouring little bits of rocks that are little particles that are suspended in air or water and going over and over other larger rocks, that abrades them, wears them down, kind of like sandpaper does to wood. 3, biological. The roots of plants can grow into the cracks of rocks and force the cracks open. Even if just the root just gets in there a little, then water can get in there also a little bit, and then that water can do the freeze thawing, but the root can also expand as the rock starts to break down, so it really snowballs in that sense. And exfoliation. Rocks on the surface are worn away, expanding gradually, those layers on top, and then cleaving off from the mother stone or rock, and the layers fall off. And if you have spent any time driving around the Sierra Nevadas, you can see this on a large scale, big, huge slabs of granite sloughing off, exfoliating off of even larger parent chunks. This is an example of biological weathering. These are a bunch of different lichen types, species, all growing on this conglomerate rock, which you see the white chunks in and the brown matrix. These lichens are a combination of 2 different species, lichens and algae, and there are also some bacteria in there. But those grow on the rock. They're the very first thing that can actually grow on that rock. You can't get grass or trees growing on that rock. First starts the lichens. They do that initial step, and they release acids which decompose the outer layers of that rock, and they break it into smaller particles, which eventually can either wash off, or if this where those lichens are growing is in some kind of crack or depression, the smaller particles can build up, as can the dead lichen and other small plants to build up organic matter. Lots of different lichens contain acids and release them to break down the rocks. And the mechanical action of the fungal threads within the lichen penetrate these small microscopic spaces in the rock crystals, and together with changes in temperature and moisture, that all combines to help break down that rock even further into what we would call soil. Same rock formation as the last two slides. These pictures were all taken at a place called Vasquez Rocks, which is kind of near Lancaster. It's a state park, and it's actually pretty cool. Same formation, pretty close to where those other lichen pictures were taken, and you can see this one had a little bit bigger crack in the rock, and the lichens might have started this and gotten some little opening and breaking down of the parent rock into smaller particles, and then also contributing some organic matter, and then a grass or some other small plant got in there, took root. Its roots and leaves add more organic matter, and you can see that this is the biological way of weathering these happening. Further down the road, if you got a little depression or a crack, you got more organic matter and minerals that have sloughed off of the parent, they've weathered off of the parent rock, and you get a fair amount of soil that can support even bigger plant, which now contributes even more organic matter, and its roots can even break up and open up the cracks even further and get water down in there. So just keeps happening. This is at the same place, Vasquez Rocks, near Palmdale and Lancaster, and where all the lichen pictures were taken. These are my two older daughters back in 2010, and the rocks here are full of holes and cracks and fissures where sediments can blow in, or lichens can take hold and start the soil formation process. And you can see these rocks are sticking up out of soil, which has been derived partially from these rocks themselves a long time ago. But great place to visit, really fun to go hike around if you ever get a chance. So aside from physical weathering, there's also chemical weathering, and it refers to rocks broken down by chemical changes within the rock, whereas with physical, it just breaks the rocks into smaller pieces, but the chemistry of each of those pieces stays the same. In chemical weathering, the rocks are broken down and are changed in their chemistry. For example, carbon dioxide dissolves in rain, forming carbonic acid, like acid rain. When it hits something like the picture you're seeing, limestone, it dissolves the limestone and changes the chemistry of what washes out of the limestone. As the limestone is worn away, calcium hydrogen carbonate solution is what is washed out. So chemical weathering is faster for limestone than sandstone, because limestone is much more porous and soft and more easily weathered in this way. And the heating process always expedites or speeds up the chemical weathering process if the weather is warmer or the water is warmer, whatever is doing the chemical weathering. Clay is formed by chemical weathering, and the clay is produced by that chemical weathering, and then vegetation can take hold in that clay. It's the very beginnings of soil, like what you're seeing here in this image of this metamorphic rock called gneiss. It's pronounced that way. And then once the clay starts to form, it's the rudimentary soil, and other things can take hold, like small grasses, moss, etc. The picture here shows at the top soil that has been weathered from limestone, or you could say it like this, limestone that has been weathered to help produce soil that's on top. And the limestone is shown at the bottom, the limestone bedrock at the bottom of the image. Limestone is calcium carbonate, And the 18 inches of soil present here, that's the darker brown stuff at the top, it originated from impurities in the rock and the addition of soil particles by wind to the surface of the soil. So you're seeing breaking down and chemical weathering of that bedrock limestone and addition of wind blown or water flowed in with sediments in it on the top to produce that soil on top. So it's a variety of processes have made that soil, and part of that is chemical weathering. This is in the middle of the United States where this soil is from. In the prairie areas, and prairie grass roots are these dark roots that go deep into the soil, and they can bring up nutrients from deep down in the soil through these cracks and bring them to the surface when those prairie grasses die back in the winter. So from years of growth and decay, growth in the summer, decay in the winter, not decaying of the roots underground, but decaying of the top part in the winter, adds more and more organic matter to the top. That's how that soil partially forms on the top of this bedrock, partially from chemical weathering and partially from this action of plants reaching deep into the bedrock and subsoil and bringing up those nutrients and creating organic matter and then dying on the top to help make the soil. In general, chemical weathering weakens the bedrock and makes it easier to break up into smaller pieces. So you can have chemical weathering and physical weathering happening together. Three of the ways that chemical weathering can occur is by hydrolysis. It's a cleaving of the chemical bonds by the addition of water. So some of the chemical bonds within the molecules of the structure of the bedrock are separated. They're broken up by water kind of getting in between those two molecules. That's hydrolysis, the addition of water to these two molecules to kind of push them apart. Dissolution is a solid broken down into separate ions and molecules in a solvent. So it's usually water that's getting onto the bedrock and breaking down the molecules in that bedrock by those molecules dissolving into the water. And the third method of chemical weathering is oxidation, and that is chemically a process where electrons are lost from the molecules in the bedrock. Oxidation, everyone knows it kind of as a layperson's process of like things that rust. Rust is an oxidation process that's changing the metal that rusts by the loss of electrons, technically, but it gives it that rust color. So physical and chemical weathering can and almost always do occur together. The physical weathering breaks the rocks into smaller pieces, so more surface area is exposed, and exposing those little pieces, more of the surface of those smaller pieces, to chemical weathering, which breaks it down even further. The weathering process, whichever of those processes we've talked about between physical and chemical, it's mostly controlled by the climate. The more water there is available in the climate, the more likely that chemical processes of weathering can proceed, and the warmer it is, the chemical processes of weathering proceed faster. And the reason is, as far as the temperature goes, is all chemical and even biochemical reactions, including the ones inside of our body, like metabolic processes, they almost all speed up as the temperature goes up. There is a maximum, like for most of our metabolic and biochemical processes in the human body are maximized around 98.6. Thus, our bodies maintain themselves there, so we have the efficient reactions, chemical reactions going on inside of us. Outside, weathering to soil, it's very similar. So usually you're seeing tropical areas that have water and warmer temperatures, higher temperatures, have faster rates of weathering and sometimes faster rates of soil buildup. Not always though, because like for example in the tropical rainforest, the soils are usually pretty thin, and that is because decomposition rate is fast from the biomass, like organic matter that comes down from the leaves and trees and things that die and fall to the ground and decompose. But there's so much vegetation that the all of those nutrients and organic matter gets dissolved and decomposed and sucked right back up into the plants again in the form of nutrients. So there's no dormant season like in a prairie system. You've got a lot of growth, above ground grasses and prairie plants, and then they all die back in the winter. So it kind of builds up a little layer of organic matter, and then it happens again and again. But in the rainforest, it's just growing all the time. So there's not a lot of time for the soil to actually accumulate. So it's a little bit different. But again, this slide is trying to tell you in general that the warmer it is and the wetter the climate is, the more weathering will occur, and theoretically more soil formation. In arid climates, it can be hot, but because there's so little water, weathering is not a very significant process. It occurs very slowly, and if any process is going to happen, it's mostly physical weathering that happens because there's not much water, and chemical weathering requires water for the most part. But because physical weathering relies on chemical weathering, it will also be quite slow in the desert. By looking at sand grains, you can determine the kind of rocks that physically weathered to make the sand. You can look closely at them and derive and understand their origins. And the weathering of rocks produces soil particles. I've said that in a number of ways so far in this lecture, but just to give you an idea, they're breaking down, the weathering is breaking down the rocks into smaller particles, some of which become part of the media or part of the soil, which can support plants well. There's something we'll be talking a few times about in this class, and that is soil texture. So if you took all the particles in a soil sample and divided them up into their size categories, there would be, well, it depends what discipline you're working from, soil scientist or farmer, agriculturalist, but they're mostly the same. The very smallest particles in the red, looking on the slide, with diameters of less than 0.002 millimeters. Those are considered clay particles. The middle range size of a soil particle is called silt. It's from 0.05 to 0.002 millimeters diameter. The largest of the three categories of soil is sand, and that's greater than 0.05 millimeters diameter particles. In the picture, it's showing you sand, silt, and clay, and also a big old gravel chunk, which is not really considered it's not considered one of the three soil particle sizes. It's just here for reference. So sand is very, very big. Thousands and thousands and thousands of clay particles could fit inside a sand grain. And silt is in between. So you're seeing how much smaller clay is. And even though these are seemingly arbitrary size categories, they're just going by size, because of the nature of clay and silt and sand, these three categories, the sand, the silt, and the clay, have distinctive properties and act and perform differently as a soil particle. So most of these particles that have less than 0.002 millimeters, they are considered clay, and they are all chemically clay. There might be a couple of, a little bit of percentage of that are teeny particles that are not clay, but almost all of it is. So we can measure the texture, and the texture of a soil is the percent of sand, percent silt, percent clay in a soil. If you added the percent sand and the percent silt and the percent clay of a soil, it would always equal 100%. So this is all this texture is looking at the relative percent of those three size classes. We will talk more about that, and you will do a soil texture test yourself. Silt grains, this is the intermediate size soil particle. In the sediment sample, the grains are a little smaller than in the sand photos, so they're magnified here. It's an electron micrograph or electron microscope picture. They look bigger because of magnification, but they are definitely smaller than the sand, a lot smaller. Silt particles have diameters between 0.05 millimeters to 0.002 millimeters. Clay particles are smaller than that, and sand particles are greater than that. Most silt grains, so little silt particles, are quartz because they're less resistant to minerals. They are less resistant minerals and have been completely broken down. So what it means is if you've got some minerals in a piece of rock, it will break down until it kind of hits the chunks of quartz, which are really hard for weathering to break down, so they remain that way. So most silt particles end up being quartz because they don't break down any further. Silt feels very smooth, by the way, and we will do a texture test by feel. And when you have a soil that feels kind of gritty, that's usually a sandy soil. A soil that feels kind of slippery, that's silt. And clay is very slimy, somewhat slippery too. So silt is created from processes of weathering, chemical and physical weathering, like abrasion, that can split very small sand-sized quartz crystals. So silt is created, even though the quartz is very resistant, it can be somewhat broken down. It usually gets to a smallest silt-sized particle, and then those processes can't break it down any further. But it is broken down a little bit from bigger chunks. And silt's composed mainly of quartz and also another mineral called feldspar, which is pretty resistant to being weathered as well. Silt is sometimes called rock flour or stone dust. And just for fun, showing you that silt has sometimes been used as an ingredient in soap because it is like a gentle abrader. So it will do some abrasion, you're kind of exfoliating the outer layers of your skin, but without really hurting you or damaging your skin. And this is supposed to be silt that was from glacial waters and put into this soap for something that hopefully sells well, but just as an example of a use of silt. The Mendenhall Glacier in Alaska, you're seeing the gray water that's coming out of the melting glacier, and the sediments on the surface of the glacier are from the grinding action of the ice on the rock, producing smaller and smaller particles. This is mostly physical weathering that's happening here, but the silt and some chemical, but first just physical of the rocks breaking by the ice abrasion. But the silt is suspended in the water for a while because it's a smaller particle, so it doesn't fall out as quick, and you get a cloudy grayish water coming out because that's the silt. So if you think about it, silt is your middle-sized particle. If you took a handful of soil, and all soil has some percentage of sand, silt, and clay in it, and you threw it into let's say a jar of water, and you'll do this test. Let's say you put your scoop of soil into a jar of water, and then you put a lid on it and you shook it up, and then you wait. The first things that will fall out to the bottom of that jar are sand, because they're the biggest particles. They're the heaviest. They'll fall out within about 30 seconds. If you waited a couple more minutes, most of the silt then falls out. And so then now you see a layer of sand on the bottom and then a layer of silt on the top. And then the clay is the smallest particle. It'd be like throwing flour into water. It would take, it takes a couple of days, if not a week, for all those clay particles to settle down onto the bottom of that jar. If you did wait that long, you would see nice bands of sand, silt, and clay. That's the way the jar test works. You can measure the percentage just by doing that process that I just described. In a real world system like this creek in the images, you'll know that where the water is moving the fastest is usually the deepest parts of the creek or river, or it could be the areas where there's a sharp turn. But any part of the creek where the water slows down, you're going to have the sand drop out, but the silt and the clay might stay suspended even longer. Well, they will stay suspended longer than the sand, so you have to have more slow moving water or little eddies sides of the creek where there's little still waters for the clay to really settle out, and even the silt. Because if the creek's moving fast, the clay will stay suspended for a long, long time, maybe all the way till it gets to the river mouth. So silt in the water will remain suspended until the water is moving very slowly. That's very true for, even more so true for clay. And the silt causes water turbidity, so that can be a problem, and it can get inside the fish's respiration system, the gills, and harm them. And now the smallest of all particles, clay. This is an electron micrograph also, but even at higher magnification of a clay particle. The flaky nature of clay particles you can see, and this is lots and lots of layers. If you've ever eaten something called baklava, it's a Greek dessert. It's made of layers and layers of thin dough. Well, a clay particle is similar in the sense it has all these layers, and because of that, tons of surface area. So lots of places for nutrients and water to hold on to, or them to hold on to each other. In your jar test, or in a creek or river or lake or ocean, clay is the last sediment to be deposited because it's so small. It has to have really still, slow waters for it to sift and filter down to the bottom. Clay particles are made not from broken down bigger pieces, but a recombination of minerals synthesized from other elements, not from grinding up of silt particles. So sand is ground up, and some of that does become silt, but ground up silt doesn't become clay. Clay is created and synthesized just naturally from other processes that recombine different elements. Clays have diameters, as I said earlier, of less than 0.002 millimeters. Soils that are high in clay, usually over 30 to 40% clay, are heavy, sticky, when they hold on to water for a long time, but when they dry out, they crack and are very hard. But they can hold a lot of water and a lot of nutrients, but they don't let go of those two things very readily. So that's why it's best to have a little bit lower, like, less than like 40%, less than 40%, more around 25% clay in texture would be best. So you have enough organic matter and you have enough silt and sand in there to kind of get between all those clay particles so they don't all stick together and hold on to each other and hold on to the water and nutrients and prevent the plants from getting those. Now let's go back to the very first slide, the picture of the tree roots with the rocks in it. Why are the rocks there? How'd they get there? Where are they coming from and where are they going? Very philosophical questions. The rocks are there, we could say, are just waiting to be broken down further into sand grains, and those later into silt grains, and maybe even eventually chemically weathered and altered into clay particles if the processes of weathering have enough time and the right environment. The rocks were probably brought there by alluvial action, meaning creeks, rivers are washing them down from higher areas of bedrock, where bedrock's exposed, usually at higher elevations. Or the weathering of bedrock, like we saw in the limestone picture, that's below, and them sometimes being pushed up. Sometimes this process called frost heaving is really interesting. I saw it a lot when I lived in the Midwest, where you get snowy, cold winters, and when I lived at high elevations, like in Big Bear. So where you get the soil freezes at night and then it thaws during the day, and that happens over and over and over, and it pushes rocks literally to the surface. That could be a reason these are here too, but we don't know for sure. But those are some of the possible options of why those rocks are there from the processes we've talked about. What are the factors that influence soil formation? So here are the five big ones. The parent materials, so the bedrock that's under there. The climate, like I said, water and heat and temperature. The living organisms there, vegetation, that's the biota. The topography is going to also influence soil formation. You don't get soil formed on the top ridges of high mountains. You get it formed
in the valleys, because that's where the water washes down sediments and organic matter and fills in the valleys where they get where the soil particles accumulate. So that's topography is going to affect it. And then the period of time since the parent materials were exposed. So this is a longer term geologic kind of factor. If you have thousands and hundreds of thousands of years that have passed since this bedrock got pushed up from geologic action and exposed at the ridge of a tall mountain, then there's time for those things, the processes to break those rocks down and form soil slowly. But if it's very newly exposed, like say a volcanic eruption, there's not really time for soil to be exposed, so it needs more time. So you might not see soil there. So those are different factors, the 5 that influence soil formation. Let's talk about each of those. Starting with the parent materials, a bedrock weathered in place, could be organic soils, are derived from the plants giving organic matter. That's what that means, organic soils. Or volcanic soils. There is soil that can be transported, that's loose material from glaciers or rivers, bringing down soil sediments and rocks in alluvium. And there's gravity deposited, wind deposited soils. Most of coastal California is sedimentary parent material, and then processes of weathering, mostly chemically, and the vegetation itself will help or make or break whether soil forms rapidly or not. The second factor we'll talk about is the climate. Precipitation is the most important factor, whether there's water and how much water. The temperature is important too. The warmer it gets, the faster the processes occur. But if there's no water, it won't matter. Like in the desert where it gets really hot, but there's not much water, so very little weathering happens. So precipitation, the most important. Effective precipitation in this scenario means the annual precipitation plus the seasonality of the precipitation, the temperature when it comes, evaporative losses, the topography, and the permeability effects. So think of this example. More rainwater will infiltrate and leach through a coarse sandy soil than a clayey one. Sandy soil experiences greater effective precipitation and more rapid soil development. So that's what effective precipitation means, is taking how much water comes down as rain or snow, but also the seasonality of it, the permeability of that soil, temperature, and all those things affect soil formation and the fertility of that soil. Effective precipitation affects the rates of chemical, physical, and biological weathering. Temperature, of course, important too. It affects the types of vegetation that can grow and the reaction rates of these weathering processes as well. Biochemical reactions, just kind of as a side note, temperature changes those. For every 10 degrees Celsius rise in temperature, the biochemical reaction rates double. So it can affect growth rates of plants, which affects biological weathering, and it can also affect chemical reactions not related to living things and speed those up. Temperature, I'll go a little bit more into that. The influences of chemical reaction rates, so things that influence those reaction rates. So this is just going into more geeky detail about the how temperature affects reaction rates and how that could affect the weathering and soil formation process. So this is just still part of the factor of climate and how climate is important in soil formation. So you could probably skip this slide if you don't, because I won't ask you much about it, but sometimes I feel like the details can help you understand the overall concept. Some people need to know those details to know the bigger picture. Some people don't. So the influencers of the chemical reaction rates, the nature of the reactants, if it's an acid or a base, usually are faster, if they have covalent bonds between the elements or molecules in that reactant, those will be slower reactions because covalent bonds are really strong and they're hard to pull apart, so they're going to be breaking the rock down more slowly than an acid base. Physical state, the more surface area in a certain kind of material, if it's solid or liquid or gas, the more surface area, the faster that reaction rate will occur. So solids, like rocks, are going to be slower than liquids and gases. So that's just in general. We're not talking just about soil and bedrock here, but it's kind of saying that it's a slower process. But temperature will affect that. So temperature will increase the reaction rates, but solids are still going to break down slower than liquids and gases. I think that's all I'll say about that slide. You can read the rest if you're interested. Okay, and the living things, the biota, another factor influencing soil formation. So the more vegetation, the more accumulation of organic matter, because little leaves fall down, plants die, roots grow and die. They're adding dead vegetation, which is organic matter, which helps build the soil. Cations, that's how you say that word. Those are positively charged ions or elements that are plant nutrients, like nitrogen or phosphorus or magnesium. These are all things plants need, and they get these nutrients from the soil. And some of them that are positively charged are called cations. So things like that, the trees suck them up and they bring them to the surface from their roots and they add them to their biomass, and then when those leaves or sticks or branches or roots die off, they add them to the soil. So that will definitely affect soil formation. Animals tend to break up the horizons too, those different layers of the soil. Those underground dwelling mammals and things really churn and mix up the soil, and that can help build soil. Ants, termites, and earthworms, and of course humans affect the soil quite a bit by their processes. Sometimes for good, the soil improves, but a lot of times it erodes and becomes less healthy. The topography of the soil is also an important factor in soil formation and weathering. The slope, the steeper it is, the more erosion, and you have less developed soils on steeper areas. Valleys, where they aren't so steep, is where the eroded material often accumulates and you get soil formation more quickly. The aspect is the direction that slope is facing. Is it facing north, south, east, west? On south-facing slopes, like we have in our front country here in Santa Barbara, our big mountains are facing south, and those are usually warmer and drier than north-facing slopes here in the northern hemisphere, and so you get less vegetation on the south-facing slopes, and you get less organic matter and slower soil building up and just less rich and less moist soils. North-facing slopes tend to be cooler, a little shadier, wetter, and richer. The soils build up more quickly, and things like oak trees can grow well in canyons and north-facing slopes, but don't do well on the south-facing slopes around here. Mainly not because they can't handle south-facing slope temperature and weather, it's because when they're little acorns, when the acorns germinate on a south-facing slope, they don't get enough water to get established. If they did, they could handle it pretty well, but if they need that first year is what they usually don't make it through on a south-facing slope, but they can in a canyon or north-facing slope. And last of the factors is time. As I talked about when I was introducing this idea, the longer soil has been forming, the thicker it becomes and the less it resembles the parent material. The little just timeline here, let's say you have barren soil. The first 100 years you have lichens and mosses on bare rock, so this takes a while. Next several hundred years you might get grasses, shrubs, and short trees that was once that bedrock. An A horizon and C horizons form, and the next 10,000 years or more forests establish. You get some soil organisms. The O horizon develops, A horizon or topsoil thickens, and then if the parent materials are the same and the climate are the same, but the timing is different. So this is a way to give you a real contrast and show you that time matters. The development of the soil profiles can be really different. So in the central north US, like Indiana, you've got soil that's been around for about 8 to 14,000 years. So the bedrock was exposed about 10,000 years ago. And it has a lot less clay accumulation in the B horizon, and the soil profile is not nearly as thick as that in central Illinois, where the soil was exposed. The bedrock was exposed and started soil formation about 100,000 years ago. So everything else is the same. The climate, the parent material, it's just the amount of time is why these two soil types are so different. So briefly and just for fun, we'll do some soil classification talk here. It's just how soils are labeled and classified. It depends, like I said earlier, kind of what your professional field is. If you're a geologist, you're going to use the Wentworth scale for classifying the soils you're working with. If you're a horticulturalist or a farmer, you're going to use the USDA scale. If you're a city planner involved in road construction, you'll use the BPR scale. There's one that's used in the ceramics industry called ASTM. Highway engineering, AASHTO, and there's the USC for civil engineering. So, it's just, these are functional classifications, meaning the soil doesn't care what it is, it doesn't have its own names. It's just how we need to categorize it for how humans are going to use it. So in agriculture, let's talk about that. That's the USDA scale, and horticulture. So in the USDA scale, that's the texture scale that I already talked to you about. So the USDA scale intentionally sets the silt clay boundary at 0.002 millimeters diameter for those particles. If it's below 0.002 millimeters diameter, it's considered a clay particle. If it's above 0.002 millimeters, it's considered a silt particle. And that is a lower silt clay boundary than the Wentworth scale and the ASTM scale. And that is because with soils that are going to be used, and we want to understand how they're going to perform for plant support for your agricultural fields or horticulture, it makes more sense, and it works out better to have those bigger particles near, like around 0.002, put into a little bit above 0.02, like 0.003 and 0.004. Those ones are better put into the clay category, and then you get a more accurate read on what is actually clay, which can tell you how well it can support plants. True clay particles, usually a fairly consistent group for particles less than 0.002 millimeters diameter, have chemical properties that allow them to hold on to and exchange important plant nutrient ions. So if we were use the Wentworth scale and you were a farmer and you did your texture test, you might get a number for clay that's a little bit bigger. It might show that you have 30% clay, because you're including those particles between 0.002 and 0.004 into clay, and that would not help you, because those could be these quartz and feldspar particles that are silt that don't have the ability to hold on to and exchange important plant nutrient ions. So again, way geeky details on this USDA scale, but again, I think if you are going to go forward in this profession, it's good background material to have to really understand what texture means. You will do a soil texture test, and I think it's a great one to do, even if you're going to go do your neighbor's, redesign your neighbor's front yard, or they're asking you, they want to put in raised beds in their backyard. Is their soil good? So it's a very common practical thing to do, a texture test. How you interpret it is going to be where you really shine and show that you understand what this means as far as what needs to be done to improve their soil and how it will perform for supporting the plants they want to grow. Okay, the next few slides are getting even further into the nitty-gritty of soil. So I'm going to kind of guide you through this. I don't want you to know all of this, but a little of it. So let's look at this slide. It's showing you a nice image of a well-developed topsoil. That's the darkest brown. And then a subsoil. That, the topsoil would be A, and the A horizon. Under that, a little bit lighter brown, the B horizon, called the subsoil, and usually has a little bit of organic matter in it, which makes it darkish, but the A horizon has the most organic matter in it, and that makes it the very darkest. And then you've got other layers. You've got your C horizon and the bedrock. Soil scientists use this word called epipedon, which means diagnostic soil horizon. So it's like they would look at what is the horizon that is used to like typify or diagnose what is this soil and how is it going to perform. A soil scientist would look at certain layers of the soil. Again, just hold what I'm saying loosely. I mostly want you just to look at that and kind of start to recognize these horizons and what they're called: A, B, C, R, O horizon on the very top, and what they're called. So if you're looking at diagnostic soil horizons, so for different types of soils, this is all over like North America, for example. You've got molic epipedon, so those are certain kinds of soils that are dark and thick and soft. They form under grasslands like our prairies. I used to live in Ohio, and that's considered part of the breadbasket of the United States, meaning those are the deepest, richest soils where most of the food for the nation comes from. A lot comes from Central California, where we have molic soils as well, because they're formed under thick grasslands. The whole Central Valley used to be all wetland grassland of California, that is. So let's just skip down. There's just different definitions. You won't run into these much unless you go further into soil science. A little more practical are looking at soil orders. All of the soils of the world are assigned to one of 12 orders. Assignment reflects the development of the soil and also that diagnostic horizon. So, and we already know that the temperature, precipitation, weathering affects the soil formation, and thus what soil order we will fall into. Here's a map of the different soil orders throughout the world. And if you look really closely, you can see the prairie and central United States are green, those mollisols that I just mentioned before, forming under grasslands like the prairies, Indiana, Illinois, Ohio, lots of other areas up through around the Mississippi Delta, rich, deep soils that most of them have been converted to agriculture and are really good for agriculture. You can kind of see in California, we've got some mollisol soils in the Central Valley. It's too small of a map to see much more, but just giving you an overview of soil types, soil orders. Here's just a list of those orders, giving you a little background to them. If you want to just focus on California, we have soil orders called aridosols. Those are dry soils in the deserts, a lot of the western United States. Dry climates, they usually have, they're alkaline, have lime and gypsum in them. Sometimes salt layers accumulate. A lot of the deserts in California are aridosols. Some other soil orders that are pertinent to Californian agriculture and horticulture. Vertisols are dark soils, have a higher percentage of clay. They do crack if they dry, and they need wet and dry seasons to develop. So the Central Valley of California is made up of a lot of those, and a lot of those were formed from deposition. A lot of Central California, like I said, was grasslands and wetlands. There were a lot of water and wet areas where a lot of sediments accumulated and built up and made these high clay soils that are now drained from farming, and very clay-like soils that if they don't stay hydrated, they crack. And then central U.S. plains and central California, I already said, are mollisols. Some more, just going through some other soil orders. Down at the bottom, oxasols. If you've ever been to Hawaii, you've seen these really reddish soils. That's aluminum oxide, clays, and iron that make them that way. So we have oxasols in Hawaii. And lastly, looking at some soil types. The prevailing climate, of course, has the control on soil formation and types. Soil types in the U.S. can be roughly described as two: pedalfers in the eastern half of the United States, and that is the soil has a lot of aluminum and iron in it, and pedocals in the drier western United States. That's the soil that has a lot of calcium in it. So pedo meaning soil and cal for calcium, and there you go. That is the description of soil formation.